Hi guys, welcome to today's lesson. So today we're going to be focusing on changing parameters of functions, right? What this means is the transformation of functions, maybe shifting a graph to the left, to the right, shifting it up, down, reflecting it about a certain axis, maybe the x-axis or the y-axis. That's really mainly what I'm going to talk about. But before that, we just need to look at a quick recap of big ideas that we need to look at under this particular topic. So let's just jump right into it. Now remember that with functions there are different types of them, which is linear, quadratic, hyperbolic, and the exponential one. So there's what we call the notation of a function, which we just quickly gonna look at what exactly it means, and then the definition of what a domain and a range is. Now, those will be our keywords, which is the function notation, the domain, and the range. Remember that when we talk about function notation, it's normally what we use in order to represent an equation of a function instead of using y when writing the equation of a function, right? So for example, I would then say f of x is equals to x squared instead of saying y is equals to x squared. And the main reason for using this f of x and the g of x and the h of x is because at times on the same system of axes, you will be required to draw many graphs. Now, if you're drawing many different graphs on one set of axes, you can't call them y is equals to y is equals to y is equals to. Then there won't be any distinction between which function is which. So if I have 3, then I can say the other one is f of x, the other one is g of x, and then the other one is h of x. Then I know for a fact that I'm talking about 3 different graphs that are drawn on the same system of axes. So please do understand, that's the main purpose of function notation, so that there's not that much ambiguity with which function am I focusing on. Also, the domain of a function will be the set of all the input values for which the function is defined, right? When I talk about the function being defined, it means where the function can go, where it can cross, where it can intersect. And then the variable that is represented or that is representing the input values is normally referred to as the independent variable, which is normally on the x-axis, right? And then when we talk about the range of a function, this will be the set of all the output values that result from the input values. Because remember, input will be the independent variable. Therefore, this one will be called a dependent variable, and it's normally on the y-axis on the Cartesian plane. Now, in specific, to look at the changing of parameters, we're going to focus mainly on the quadratic function, which is normally called a parabola. So remember that a quadratic function is a function of the form f of x is equals to ax squared plus bx plus c, where the a, the b, and the c are constants, right? They can be any real number that is there in mathematics. They don't represent anything specific. And then the graph of a quadratic function is normally called a parabola. Also, the quadratic function can also be in the form f of x is equals to a open bracket x plus p all squared plus q, right? Where the p and the q are the coordinates of the turning point. So in simple terms, if you know what your turning point is, your very first thought will be to look at this particular equation in order to maybe find the equation of that particular graph, or to then actually tell what the turning point of the graph is. But with the other one, it will be mainly when we want to talk about the root, which are the x-intercepts, which I believe by now you do know that x-intercepts will mean we must let y be equal to 0. And then we can solve for x from there. So that's what this is all about. So this is the other type of a quadratic equation that we can use to represent a parabola, given that we know what its turning point is. Now, the value of a in the equation, because we still need to know what exactly this a tells us, right? The others are constants, yes. Even a is a constant, but it tells us what the orientation of the graph is, and it also tells us the closeness of the arms of the parabola to the y-axis. In actuality, it means that if my a is greater than 0, meaning it's positive, right? Therefore, the parabola will then be concave up, which we use a happy face as a representation, or rather as an explanation of what this is, because it is looking like a happy face, a smile. And then when a is less than 0, the parabola will be concave down, which then means it's a sad face. So just so that you can remember what it looks like. Remember, I said again, it also talks about how close it is to the y-axis. So the greater the value of a, the narrower the graph becomes. In simple terms, the more close it gets to the y-axis. Just to show you what this means, if maybe my graph is y is equals to x squared, it will look like this, and then it becomes 2x squared, and then it becomes 3x squared. So as a is increasing, it means that the graph will become a bit narrower in terms of the distance from the y-axis. Just so that we can look at a specific question now of this, how do we change these parameters? The first question will want us to draw a graph of f of x is equals to x squared. And then we'll go down with the questions to see what it will end up as at the end. To draw the graph, remember that the very first thing to always try and do is to find the table of values, right? Where you choose your own inputs. But the input, if you take from -2, you can take up until +2, and then find the output values using the equation f of x is equals to x squared. And then after drawing the graph, it will therefore look like a happy face number 1, because the value of a is equals to 1, and that's a positive, so it must be concave up. And then because it is x squared, it means all the output values will definitely be positive. We then need to reflect this about the x-axis, and to do that, it means that because the function was f of x is equals to x squared, when I reflect this about the x-axis, it will be minus f of x is equals to x squared, which eventually becomes f of x is equals to negative x squared. So in simple terms, it now becomes a sad face instead of the happy face. And therefore, the graph will look like this. And then you will also need to shift the graph 1 unit left and 3 units up. So just to go back to what we had, right? Remember that the graph was turning at 0 and 0. Firstly, you shift it 1 unit to the left. So it means it will now be turning at -1 and 0. And then after doing that, you shift it 3 units up. So it will be at -1 and 3. Therefore, my turning point will be at that point there. Now, they will also want us to write the equation of the new function. To do that, you need to look at how did we form g of x. We formed g of x by reflecting the graph of f about the x-axis, which made it to be negative x squared. And then from there we shifted it 1 unit left, and shifting it 1 unit left will make it negative x plus 1 all squared, and then we shifted this 3 units up, which will mean it will be plus 3. Now I know some people are going to wonder why is it plus 1 and not -1, because to the left is minus. But it simply means that it's y is equals to -1, right? Because x is equals to -1, that's where it lands. So the new turning point will be x equals to minus 1. If I want to write it as x plus p, it will be x. Then the minus 1 is taken to the other side, therefore it becomes plus 1 equal to 0. That's where the plus 1 comes from. And therefore, my equation will then be g of x is equals to minus into x plus 1 all squared plus 3. Just to summarize what we know about these two functions, the value of a for f of x was 1, and the value of a for g of x is now minus 1, right? Because it was reflected about the x-axis. The turning point was at 0 and 0 for the graph of f of x, and now for the graph of g of x, it was moved 1 unit to the left, so the x value is now minus 1, and it was shifted 3 units up, so the y value is now positive 3. And the domain is x is an element of real numbers because it can be any number because of the squared, and it does not change even with the g of x. But what changes is the range. Here with this graph, remember it was above the x-axis, so it means all the y values are positive, and this one will then be less than 3 because that's where it will be tending to face down. So that's what you need to look at. When you are shifting a graph, you just need to look at what will be the new value. That's what will inform you to write the new formula. Guys, I hope you're having so much fun, but for now, I want us to take a quick ad break and we'll come back with some more work to do. Please stay tuned. Hi guys, welcome back. We are still looking at changing parameters of functions. We've looked at a quadratic function and we try to see what exactly it is about when we are trying to change the parameters. Now, we are going to look at a hyperbolic function, which is a hyperbola, rather, the short way of the actual curve itself. So let's just jump right into it. Right, so remember that a hyperbolic function is a function of the form f of x is equals to a over x plus p plus q, where the p and the q are the asymptotes of this particular function, and the a value is just a constant, right? Remember, we do know what this constant what it does for us, right? It normally tells us things about orientation and about the shape where the parabola is going to, the hyperbola is going to be. So the graph of a hyperbolic function is normally known as a hyperbola, right? Now, if a is greater than 0, the graph normally lies in the first and the third quadrants. Remember, this is my first quadrant, that's my second quadrant, that's my third, and that is my fourth, right? Now, just to explain what this means, if a is positive, because remember that greater than 0 means positive, it simply means that the gradient, although we don't really talk about the gradient with a curve, but the gradient, which is normally change in y over change in x, is a positive one. Why? Because the y values here are positive and the x values here are positive. So either when you multiply them or divide them, you will always get a positive as your answer. Even with the third quadrant, because the y values are negative and the x values are also negative, when you multiply them or divide them, your answer will always be a positive. So that's why the graph will then lie in the first and the third quadrant. But if a is less than 0, which means negative, the graph will then lie in the second quadrant and the fourth quadrant. And the reason is still the same, is the fact that the y values here are positive and the x values there are negative. So multiplying them or dividing them, which has the same effect, will result in a negative answer. Similarly with the fourth quadrant, I have positive x values, I have negative y values. If you multiply or divide them, it will definitely give you a negative, which has the same effect. Now, someone might ask, why is this important? It is important because just as I give you the equation and I want you to sketch a specific graph for me, you can already have an idea of where it is going to be placed without you finding the table of values first or the intercepts or anything like that. Already you'll have an idea that my two arms need to either be on the first and the third if A is positive, or the second and the fourth if A is negative. So it already gives you a kickstart to say, I know exactly where my graphs is supposed to be. The next step will be then find those values that you are going to plot and join them with a curve. So that's why this is actually important for us to know what the A tells us about where the graph is going to be located. Also, the value of A in that equation also determines the vertical stretch of the branches of the hyperbola. As much as it talks about the orientation of the graph, it also tells us what the vertical stretch is, right? Meaning, the larger the value of A, the further the stretch. In simple terms, the steeper it is, although it's not really a line. Now, to demonstrate this, the first graph, we can say this is 1 over x. And then the second graph, we will then say this is 2 over x. So the value of A is increasing as you're going from left to right with this particular demonstration. And then the third graph will be when I have 3 over x, right? So you can see my value of A was 1, it became 2, and then it became 3. So what this means, as A is increasing, the graph is also becoming more steeper, right? Or it becomes a bit further from the y-axis, which is what the value of A tells us in terms of the shape of the graph. Now, the value of Q, which is the asymptote, this determines the shift of the graph up or down, right? It also represents the asymptote, which is normally represented by a dotted line. Now, what this means is if I have a graph like this or a Cartesian plane, and I say my graph lies there and the other arm lies maybe here, then my asymptote will be lying at that point there, and that's how I'm going to represent that is an asymptote, right? Because if I draw a solid line, then there won't be a difference between the Cartesian plane and the asymptote. So we use a dotted line to represent that this is the asymptote. And if you may just remember, the asymptote will be where the graph can approach but never to touch or cross that particular line. And then the value of P will be the very same thing, which is the shift of the graph, but now instead of it being up and down, it actually becomes left or right, and this is also the vertical asymptote of the graph. So maybe it will be at that point there, and it will be represented the same way as the horizontal asymptote using a dotted line. Now, just to have a specific example of where we see what this is all about, let's consider the graph f of x is equals to 1 over x. First thing I want us to do is to draw the graph. To draw the graph, remember the easier way of doing this is just to figure out what is the table of values, where you have your input values and your output values. Your output values, you get them from the input values, because remember it's independent and dependent variable. Now you can see that x can never be 0 because the equation is 1 over x. So if x is a denominator, definitely this will be undefined. Because a is positive, right, which is 1, already I know it must be in the first and in the third quadrant, right? So already I know something about this graph. And then I can plot my values just as I see them, that minus 2 goes with minus 1 over 2, which is somewhere there. Minus 1 goes with minus 1, which will also be somewhere there, and then you join them with a curve, and then you must show arrows at the end, because these arrows represent that this graph is continuing indefinitely, right? But it will never cross the y-axis or the x-axis, and it simply means that we can say our asymptote here is on the y-axis and it's on the x-axis. The second thing I want us to do is to reflect this graph about the y-axis, and to do that, it simply means the equation was y is equals to 1 over x, right, which is f of x. If I reflect this about the y-axis, the x will become a negative, so it will now be 1 over negative x, which is the same as minus 1 over x. So now the value of a is now a negative, which means second and fourth quadrant, right? So that's where it will now be. It will still be the same graph, but in the different quadrants. Then we need to shift this 2 units left and 1 unit up. To do that, it means from it being at the origin, it will move 2 units left, which will be now at minus 2, so that will be my new asymptote, and then it will also move 1 unit up, which will be at 1, and that will be my new asymptote. And then write down the equation of the new function. Remember, the new function was formed by reflecting f of x about the y-axis, and then by also shifting it 2 units left and 1 unit up. And therefore my equation then becomes x plus 2 and then plus 1 at the end there. Now, just to summarize what we know about this, remember our original equation, right, was f of x is equals to 1 over x. And the graph was on the first quadrant and in the third quadrant. Our asymptotes were the axis of the y-axis and the x-axis, right, of the Cartesian plane. So it was x equal to 0 and y equal to 0. But the graph was now shifted 2 units to the left. So instead of it now becoming x is equals to 0, it moves 2 units to the left, which will land at minus 2. Hence, the new asymptote is now x equals to minus 2. And then the y asymptote was at y is equals to 0. This also shifted 1 unit up. It became y is equals to 1. Now, the domain quickly is x can never be 0, right? Because it cannot cross the x-axis, at the y-axis that is. But now, with the new function, it cannot cross minus 2. And then, although all the other values are existing, or the graph is defined on, hence the x is an element of real numbers. And similarly with the range, it's the same thing, but with the new one, it's actually 1 and not 0. And that's how you then analyze and interpret two graphs that you have changed parameters of. All right, guys, that's it for now. I believe that you are still enjoying everything that we are looking at, but I just want us to take a quick ad break just to refresh a bit and look at the work that we've done and reflect a bit, so that when you come back, you know maybe what to look for and try to see where you are still lacking some understanding. Please stay tuned. I'll be back just after the ad break. Hi guys, welcome back to our lesson. We are still looking at changing the parameters of different functions, right? We've looked at two two functions, which was the quadratic function and the hyperbolic function. Now we need to look at an exponential function to try and see, when we're changing the parameters of that graph, what exactly happens to that particular graph and what will be the new equation based on those changes that we'll make there. Let's just jump right into it. Now, remember, an exponential function is a function of the form f of x is equals to ab to the exponent of x plus q. Now, you will see that some textbooks also use f of x is equals to ab x plus p plus q, right? Just to represent a constant there of p. It really does not mean anything. It's normally just a constant. What is mostly important is what the q does, right? Although with the other letters, they also do tell us a few things. Now, the exponential function only has one asymptote, which is the horizontal asymptote, right? So you can never say an exponential graph has a vertical asymptote, because an exponential graph is normally something of that nature. If you say a vertical asymptote, you're saying, I'm cutting it here, because then it won't make sense. And you can't even cut it there because it is no longer an asymptote since it crosses through the actual graph. Now, the value of a in the equation determines the vertical stretch of the graph, right? What does that mean? As a increases, firstly, we can say that this is y is equals to 2 to the exponent of x, right? Because it's an increasing function. And then we then say this is the same as y is equals to 2 multiplied by 2 to the exponent of x, right? Here the value of a was equals to 1. Here the value of a is equals to 2. And then the third graph will be when is y is equals to 3 multiplied by 2 to the exponent of x. Now a here is equals to 3, not 1. Now you can see that as we moved from left to right, the value of a was increasing. And as it was increasing, the graph was stretching more, right? Stretching more meaning that it is becoming a bit steeper as the value of a is increasing. And I will be using the word steep, although it's not really a straight line, but a curve can also be a bit steep. So you can see that from the first graph to the second graph, it became a bit steeper by becoming closer to the y-axis, and then to the third graph, it became a bit way more close, and it was passing through different values of the y-intercept, right, when it comes to the y-axis. Now, the value of b tells us the shape and the steepness of the graph, right? So that one was about the stretch of the graph. And the stretch of the graph, in turn, the more it becomes stretched, the more it becomes a bit steeper. But now, if b is greater than 0, it means that the graph moves upwards from left to right as the x value increases. We normally call this an increasing function. And the reason we call it an increasing function is because as you are moving from left to right, because you always look at a graph from left to right? Remember, it's small to big, so the negatives are small. As you're moving from left to right, the values of x are increasing. And as they are increasing, simultaneously, the values of y are also increasing because it is going up like that. Hence, it is called an increasing function, right? But now the opposite will be true. As you're moving from left to right and x is increasing, but the y is decreasing, we then call that a decreasing function. But let me show you a sketch of how that looks. Now, this is when b is greater than 0 but less than 1, right? So an example will be 1 over 2 to the exponent of x, right? So this is called a decreasing function. and we normally have arrows there. You can see really from the board that the value of y here when x was minus 1 is 2. Then the value of y when x is now 0, which means x has increased, is now 1. And the value of y when x is equals to 1, you can see that that's a half, so it has decreased. And then when x is equals to 2, you can see it is more or less 0,1 or something of 0,2 there, right? So you can automatically see that this is decreasing as the x value is increasing. But the x is always increasing because it's from left to right. Now, I want us to sketch the graph of f of x is equals to minus 3 into 1 over 2 to the exponent of x plus 3. We first need to understand a few things about this. What does this value of a tell us? What does this value of b tell us? And what does this value of q tell us as well? So firstly, we do know that this will then tell us the stretch of the graph, right? It will tell us the stretch of the graph. But because it tells us the stretch of the graph as well, the negative, which is the sign, tells us that it is reflected, right? So this is a reflection, right? It is no longer above the x-axis, it is now below the x-axis. So that's what it is telling us, because above the x-axis, we're talking about positives, whereas below, we're talking about the negatives. And then the 1 over 2 tells us that the graph is decreasing, right? Decreasing, remember, I just showed you now, that this will mean the graph is going down from left to right, right? So it will look something of that nature. And then plus 3 tells us that the graph cannot cross the line y is equals to 3. So the value of b rather, remember, was 1 over 2. So this means it is less than 1, right? But greater than 0. Hence, this is a decreasing function. And then a is negative 3. The graph is reflected in the equation y is equals to 3. And then q is equals to 3. Therefore, the graph is shifted 3 units up. So to draw the graph, it will then look something of this nature. So remember, if this was a positive, it means that my graph will be somewhere up here, right? So it will be like this. And then I will need the 3 there, which is the value of q. But because of this negative here, this negative is what informs that this graph must be reflected in order to then become in the negative axis. But because we moved it 3 units up, it then changed the origin or the x-axis to y equals to 3, which will be our asymptote. Now, what do we do after sketching the graph? The most important thing to do on a graph is to represent the asymptote of the graph, right? When you represent the asymptote of the graph, you must even write that y is equals to 3 in order to indicate where exactly is our asymptote. Because remember, at times we say the following graph is not drawn to scale. So what you see with your eyes might not be what the next person sees. But if you both write it down, then it means everyone will see the same thing. Then also, you must also indicate your intercept with the axis, that x is equals to 0 when y is equals to 0 there. So in simple terms, you will just write them as coordinates, 0 and 0. And that's how you will then plot the graph. So remember, although we've been plotting graphs using the table of values, at times you can just interpret what the different alphabets, right, which are variables, tell us about the graph. If a is negative, it's a reflection about that particular line, right? If b is greater than 1, then it is an increasing function, meaning it is going up from left to right. If b is between 0 and 1, then it is going down. And the value of q always tells us what the vertical shift is. Where is our asymptote? Where can the graph not touch or not cross? And that's what we look at. Guys, I want us to take a quick ad break. When we come back, we are going to look at interpreting graphs on the same plane that have to do with, if I'm given two graphs on the same plane, how do I then make sense of what I am seeing based on interpretation of graphs? I'll be back just now. Please stay tuned. Hi guys, welcome back from the ad break. So we are still looking at changing parameters of functions, right? But now in specific, we are going to look at interpreting graphs of functions, right? How do we interpret different graphs that are given to us? And how do we then interpret them if it's not only one graph, it's two graphs on the same plane, it's three graphs on the same plane? How do we look at what do we say in terms of what does this mean when it's above the other one, below the other one? How do we look at that? So that's just what I want you to think about as we go through this segment. Now, remember that when interpreting graphs, you're always going to be using what we call the inequalities, right? So here we normally use the inequalities, and the inequalities will be representing positive and negative, and then will also be representing where the other one is greater than the other one. So one graph being greater or less than the other graph. The very first interpretation will be when they say to you f of x or g of x or h of x, it doesn't really matter which function it is greater than 0. This simply means that the graph is positive, because remember, the f of x and the g of x and the h of x normally represents y. So when I say where y is positive, it means I'm talking about where y is above the x-axis, right? So it's when the graph, the part of the graph that is above the x-axis. But now, if I say less than 0, which is the f of x, this will then be when the graph is below the x-axis, right? So remember, our Cartesian plane, guys, on top here has a positive value of y, and at the bottom there it has a negative value. So as soon as I talk about positive, which is greater than 0, I am saying the graph must be somewhere up here, right? But when I then say less than 0, I am simply saying the graph must be somewhere down there, below the x-axis. So that's what greater than 0 and less than 0 means. Now, when then we talk about two graphs that are on the same plane, and I say f of x is greater than g of x, this is when the graph of f is above the graph of g, right? So if I draw just a graph here to show you what this means, let's say, for example, I have a parabola like that, and I have a straight line graph like that, right? When I want the values of x, where the y of f is bigger than the y of g, I'm simply saying I want where the graph of f, let's call this one f, and let's call that one f. I want where the parabola is above the straight line graph. So you can see that here the straight line graph is above, so I'll call this a section number 1 or segment number 1, and this will be segment number 2, and that side will be segment number 3. And I will be using where the graphs are intersecting in order to name my segment. In segment number 1, you can see the straight line is the one that's above, so it does not hold. But in the second segment, you can see that the parabola is definitely above the straight line graph, right? So here, this one is above and this one is below. And in the third segment, you can then see that it's the G that's above the F. So it will only be between the A and the B there. That's where the graph will be satisfying F greater than G. But when it's the opposite, where F is less than G, it simply means that it's where the graph of F is below the graph of G. So with our segments here, if you remember, it will be in the first segment and in the third segment, right? So to write these solutions, for the first one, my solution will be X must be between the X value of B and the X value of A, right? Because it is trapped in between this arrow that I was showing you. But when it is less than G of X, it means my X value must be less than A, right? Because it's everything that's on that side. Or, because it's two sides, on either side rather, it will be X must be greater than B, because it's on the right-hand side of that, right? So just because of I labeled or I let my intersection be A and B. Now at times they might say where F multiplied by G is greater than 0. So for me to get something that is positive when I'm multiplying two things, right? Just logically think about this. I want to get something that is greater than 0, meaning positive. It means I must multiply either a positive and a positive, or I must multiply a negative and a negative, right? So, in simple terms, the two graphs must either be above the x-axis, both of them, or they must be both below the x-axis. Then this condition will be satisfied. But you need to look at the y value, right? So we use the y values more than anything. Although when you write your solution, you write it as x, because remember, you get y because of x. You remember the independent and the dependent that we spoke about. Now, in simple terms, this means that F and G must have the same sign. I did say it's either they are both positive and positive, which will be above, or they are both negative and negative, which they will be both below. So they are both positive and above, or they are both negative and below, as you can see there. The opposite will be true, and then it will be when F multiplied by G is less than 0. It means that they must have opposite signs. Really, you know, that's how you get a negative and you are multiplying. It must either be plus and minus, or it must be minus and plus. Now, in terms of the axis, it can be either, right? Or rather, they must be on either side of the axis, and that's the x-axis, right? So maybe if I draw just the same scenario with the previous example, you will look at this graph is positive there, and at the same time it is positive, this one is negative there. You see, so this is positive, that is negative. So it means if you multiply them, then they will give you a less than 0, right? But if you look at just below the x-axis here, you can see that the graph of the parabola is negative, and the graph of the straight line is also negative. So if I multiply these, I will definitely get a positive. So this will not be true. So those are just the things that you need to look at. But let's just quickly look at this in terms of practicality there, right? Now, it says the following sketch shows the graph of f of x and g of x. It's a straight line and a parabola. What will we start with? We start with labeling using a vertical dotted line, right? Labeling your intercepts of the graphs, where they're intersecting with one another, because that's what we're gonna try and use, even with the intercept with the axis. For which values of x is f of x greater or equal to g of x? Now, firstly, equal to means that where they are intersecting, right? So this is the point of intersection. I will just say it's POI, point of intersection. Then greater than means above, right? Above this one. Now, where is the graph, number one, above the other graph, and also meaning f is above g, and also where are they intersecting with one another? So you can see they're intersecting there, they're intersecting there, right? So that's at x equal to 0, and that's at x is equals to 7. And then I want it to be such that one is above the other. So my f will be the parabola. For the parabola to be above, it's that arm there and it's that arm there. So it means my x must be less or equal to 0, or my x must be greater or equals to 7. And that's where it will satisfy this condition. And then when it is less than 0, it simply just wants it where one is negative and one is positive. So you can see that from there to there, right? Here they are both positive, so I can't use that. They are both positive, I can't use that. But here you can see one is positive and one is negative, so my x must be less than -1. Now, just to summarize what we've looked at, remember a function can be transformed by changing the parameters of each function, right? Of each function, I'm talking about the parent function. You saw we changed x squared and it became a new function. We changed 1 over x, it became a new function. We changed the exponential function as well, and it became another function. Also, you need to please recall what the effects of changing a, p, and q are for the different functions. Now, there's one more thing that I want us to quickly look at, especially with these interpretations. At times you will see they will say f of x minus g of x. I just thought of this now, and they say greater than or equal to 0. This simply means you must take the g of x to the other side, and then it simply becomes f of x equals to g of x. So again, POI, point of intersection. Please remember that. So that's what you guys really need to understand there. The nature of functions has to do with the x-axis. That's mainly what we look at. Is it above? Is it below? What does that mean? Is it above the other one? Is it below it? What does that mean as well? So those are just the things that you please need to look at. And then, guys, we have come to the end of our lesson. I hope you've been enjoying all of this that we've done, but I need you to please do your own research wherever you did not understand certain things so that you can be clear, and try some examples that you find on the internet, on the textbooks that you use. Guys, remember, from me, the maths doctor, to you, mathematics is food for the soul.